The solar system, our cosmic home. Is it something exceptional? Or just one planetary system among countless others? Star systems always form in the same way, initially. But once gas planets have formed, they can have a decisive influence on the way the system develops thereafter. And the two gas giants, Jupiter and Saturn, substantially determined the course of our solar system's evolution too.
We live in a solar system that's just perfect for us. We have the perfect sun. It will shine without any major fluctuations for around 10 billion years, enough time to allow for biological life to develop. We have the gas planets, Jupiter and Saturn. They protect us from asteroid impacts. The Earth is perfect. It has just the right size and is at just the right distance from the sun so it isn't too hot or cold. We have a large moon, which stabilizes the Earth's axis. Is this all just a coincidence, or has it been specially made this way for us? Regardless, our sun is without doubt very special. It's a so-called G-star. Only 8% of all the stars out there are G-stars.
G indicates the spectral class of our sun, yellow. It belongs to the star class G25, also referred to as a yellow dwarf. The sun is something very special. It's our giver of life. In terms of size, however, it's pretty average by astronomical standards. There are hundreds of billions of stars in our galaxy alone, and the majority of these have a planetary system.
A large number of the stars we've been able to properly observe up to now have planets, and that's most unexpected. It seems to indicate that our solar system isn't anything exceptional, but rather the norm.
Our sun formed from interstellar material, primarily hydrogen left over from the Big Bang, and the remnants of a supernova, the explosion of a massive star. It was the death of this star that triggered the birth of our solar system. Scientists estimate that the gas and dust cloud from such a supernova spawns roughly 1,000 new star systems. Around 70% of these are binary or multiple star systems. Even systems like these can have planets, like the binary star system Kepler 1647, which is 3,700 light-years away.
When you have a binary star and thus a triple system with a planet, you always have a latent dynamic instability, because triple systems have a tendency to be unstable. At some point, one of the three bodies usually gets expelled. But if the two stars are close together and the planet is a long way from them, and massive, as in this case, the system exhibits a certain stability too, though it's possible for it to remain stable for a long time.
The birthplace of our solar system was a cloud of interstellar material that collapsed. Hydrogen gas accumulated in the prestellar core. Density and pressure increased. Once the core temperature exceeded a few thousand degrees, the hydrogen molecules split into two atoms and became ionized. They lost their electron shell. The enormous pressure caused the hydrogen atoms in the core to combine to form helium, the start of nuclear fusion. The sun is born.
There's naturally always a bit of dust left over that doesn't end up in the star. And once everything's rotating and moving around quickly, the surrounding dust gets spread out and forms a disk. There's now a lot of rotational energy in this disk. Most of the mass is in the sun, but the kinetic energy of a system like this is now in the disk, which orbits the sun in the equatorial plane.
There are differences in density and temperature within this protoplanetary disk. During the roughly 50 million years it takes for the sun to form, material in this disk is accreting. Lumps of material, so-called planetesimals, develop. These collide with one another and grow in size. The bigger they get, the more material they attract. In this way, Planetesimals first grow to become protoplanets and then planets, and the Earth is no exception. The leftovers from this formation period then orbit the Sun as asteroids, minor and dwarf planets. Star systems always form in the same way, but this doesn't mean that the size, type, and arrangement of the planets is always the same.
We're learning a great deal from studying planetary systems around other stars, including about our own origins. We used to think we understood how things came about. Having studied other planetary systems, we now know that things can turn out very differently. The fact is, we don't have one theory for all planets, and never have. Stars have different masses, and small, low-mass stars evolve more slowly than large, massive stars.
The shock wave from a supernova gives rise to entire clusters of stars. Scientists suspect that our Sun's birth cluster contained several thousand stars, some of which probably influenced the evolution of our planetary system. Such clusters become less and less dense with age. They thin out. Today, our solar system is in a region of low stellar density.
So where in the universe is our solar system? Like all other stars, we're part of a so-called galaxy. This is our galaxy, the Milky Way. And where in the Milky Way are we? Roughly 2/3 out from the center in a partial arm called the Orion Arm. That's here. And it's the perfect place for us to be. This region is also referred to as a habitable zone. Why? Well, if we were closer to the center of the galaxy, the star density is so great that every supernova explosion would wipe out life on Earth. Further out, there's less dust, which means hardly any rocky planets like the Earth could form. In other words, the habitable zone is the perfect place for our Earth.
Galaxies are typically collections of a few hundred billion stars, planetary systems, gas and dust clouds. Scientists suspect that there are over 1 trillion galaxies in the observable universe, and our Milky Way is one of the oldest. Researchers estimate that the first stars in our galaxy formed just 800 million years after the Big Bang, which would make the Milky Way almost 13 billion years old. Our solar system orbits the Galactic Center, which is home to a supermassive black hole at a distance of roughly 27,000 light-years and a speed of 700,000 kilometers per hour. This is Sagittarius A star. In 2022, astronomers used Event Horizon, an array of radio telescopes, to capture the very first image of this black hole, around which the Earth, our solar system, and all other objects in the Milky Way revolve.
There's an enormous mass at the center of this system. The gravity of this enormous mass is such that it attracts everything around it. And the entire structure is rotating too, which means there's a vast amount of angular momentum in the system, and that is why the stars orbit this central mass, as it were. It's like a whirlpool, and at some point they'll all get sucked in.
The picture scientists have built up of our galaxy is based on observations of the stars, our knowledge of physical forces, and comparisons with other galaxies, because we're not able to observe our galaxy from the outside.
When we look at the Milky Way in the night sky, typically in winter, we're looking at the outer edge. In summer, we're looking towards the center of the Milky Way, and that's the brighter region, where there are more stars. Because the Earth's axis is tilted the way it is, we can observe different parts of the Milky Way.
From the Earth, our galaxy appears to the naked eye as a light strip. It meanders across the night sky like a milky brushstroke, hence the name, which was coined in antiquity, Milky Way, a collection of several 100 billion stars. The large dark patches are clouds of interstellar gas and dust. Scientists are learning more and more about our galactic home, and it seems likely that somewhere in this myriad of stars, other life exists.
How common is life in our galaxy? We've recently made important progress in answering this question. Namely, we now know that planets with the same mass and radius as the Earth are quite common in the Milky Way.
The laws of physics apply equally throughout the universe. But whether or not life always forms if the conditions are conducive is uncertain.
Just because there's life in one place in the universe, namely on Earth, it doesn't automatically mean that there's life elsewhere in the universe. I think as scientists, we should be very wary about drawing such a conclusion. You might say it's likely that this is the case. But it could also be that the conditions that allowed life to originate here are so unique that they aren't found anywhere else in the universe. Having said that, the basic prerequisites for life, that is, water, carbon, and energy, seem to be present in so many places in the universe, and by water, I mean liquid water, that they must be present everywhere throughout the universe.
After the Andromeda Galaxy, our Milky Way is the second largest of 50 galaxies in the so-called local group. The Milky Way and the Andromeda Galaxy are approaching one another at a speed of roughly 430,000 kilometers per hour. They're set to collide in 3 to 4 billion years. This won't affect human beings, though, because the Earth will have long since become uninhabitable.
Our solar system consists of 8 planets. The 4 outer ones, Jupiter, Saturn, Uranus, and Neptune, are gas giants, whereby the last 2 have a bit of ammonia and methane in addition to hydrogen, which is why they're sometimes referred to as ice giants. Toward the center are the 4 rocky planets. Rocky because they have a solid surface. Of these 4, Mercury and Mars are too small, though. So small that they don't have their own atmosphere. Not good for life. Earth and Venus are the perfect size, although only the Earth is right in the middle of the so-called habitable zone. The habitable zone is just the right distance from the Sun so that temperatures lie between 0 and 50 degrees Celsius, which is ideal for life.
Mercury orbits the Sun in just 88 days. The innermost planet in the solar system is only a little larger than our Moon, and resembles it superficially too. Its surface is covered with impact craters, and like the Moon, Mercury has no atmosphere. On October 20th, 2018, the probe Bepi Colombo was launched on a mission to Mercury. The European-Japanese space probe will take 7 years to reach its destination. Scientists want to discover more about Mercury's geological past in order to better understand the origins of our solar system. Bepi Colombo is tasked with finding out whether there is water ice in the craters at Mercury's poles and studying the composition of the planet in more detail. Because Mercury exhibits peculiarities that distinguish it from other rocky planets.
Mercury formed at around the same time as the other rocky planets, Mars, Venus, and Earth. But the structure of Mercury is rather unique. Mercury is smaller than Mars, but it is very dense for its size, which means Mercury has a very large core that makes up roughly 80% of the planet's radius. It's possible that early on in its life, after it formed, there was a massive collision and parts of the mantle were stripped away.
Venus is almost the same size as the Earth, which is why it's often described as our sister planet. Venus is one of our 2 planetary neighbors and gets to within roughly 38 million kilometers of the Earth on its journey around the Sun. Despite this, Venus and Earth have little in common. Our neighbor rotates very slowly on its axis. A day on Venus takes a little over 243 Earth days. Moreover, it's enveloped by a dense layer of cloud. For a long time, we had no idea what its surface looked like. Up until the early 20th century, some astronomers even thought that Venus could be inhabited.
In the past, people thought, well, Venus is similar in size and mass to the Earth. It's a bit closer to the Sun. There could possibly be humans and animals and plants there. It might be a little warmer than on Earth because of its tropical climate, etc. But we now know from measurements that it's anything but that. The atmosphere of Venus is extremely toxic. It's dominated by carbon dioxide and sulfuric acid as well. There are simulations that suggest that around 715 million years ago, the climate on Venus was much milder. It could even have had water on the surface and been much more similar to Earth.
Venus is hot. A runaway greenhouse effect has heated the surface of Venus to almost 500 degrees Celsius. Our neighbor is still interesting, though. NASA's Da Vinci mission plans to land on Venus and during the descent, analyze the atmosphere in more detail.
The thought is that there could be a zone, not on the Venusian surface, but in the atmosphere, where there's sufficient water and where very primitive life might have evolved.
Our other immediate neighbor is Mars, the planet that probably sparks people's imagination the most. Next to the Earth, Mars is the most studied planet in our solar system. Nonetheless, it still holds many secrets. The red planet has a lot to offer the researchers. It's geologically diverse and has an atmosphere, albeit very thin. Mars has water in the form of ice at the poles and possibly underground too, which makes Mars especially interesting in the search for former or present-day life within our solar system.
We see valleys, deltas, and channels that were carved out by water, which means Mars had liquid water on its surface at some time in its past. And liquid water is a prerequisite for life, or at least for life as we know it on Earth.
Our solar system's 4 terrestrial planets are fairly close together and are small compared to the gas giants. From a cosmic perspective, our Earth is a midget. Despite this, it's the only known celestial body that supports life.
The Earth is perfect, of course, but it has certain prerequisites that make it perfect. And one of them is the Moon, which stabilizes a lot of things on Earth and ensures, for example, that the water moves back and forth. Another major factor is plate tectonics. It has consequences that we don't like very much, such as volcanism and earthquakes, but it also affects the Earth as a whole. This means the planet is able to generate a magnetic field, for instance, and it has a relatively dense atmosphere.
For us, the Earth sets the standard when it comes to higher forms of life. It offers the ideal conditions for the creation and evolution of diverse life forms. Several thousand exoplanets have been discovered so far, but none with comparable attributes.
Every astronomer is looking for Earth-like planets. But what does that actually mean? Not much, really. It just means terrestrial planet. That is, one with a solid surface. But that's not really what we're looking for. We're looking for planets that can support life. And they're actually pretty rare. It's thought that only 1 in 1,000 to 10,000 stars has such a habitable planet, which we refer to as Earth-analog planets. Despite this, in a galaxy the size of the Milky Way, which contains roughly 100 billion stars, there could be 1 to 10 million Earth-analog planets, which would make the average distance between them roughly 30 light-years.
Is there life beyond Earth? In light of the vast number of stars with planetary systems in the universe, the answer is most likely yes, including in our galaxy, and perhaps even in our solar system. And many scientists are convinced that extraterrestrial life will be discovered before the end of this century.
Of course, it depends on what kind of life we expect to find. If you were to ask, will we find intelligent humanoid creatures? Then I would say, given the list of prerequisites and the probability of life developing somewhere, I'd say we're probably the only ones in our galaxy at the moment. If you were to say a few single-celled organisms or algae would do it, we don't have to find large creatures, big fish, whales, etc. Small microscopic life forms would suffice. If you accept that, you could presumably find several thousand planets in our galaxy that meet the necessary criteria.
Finding a second Earth in the vastness of space is one of the astronomers' primary goals, even if it turns out that evolution, as it occurred on Earth, is just an incredible cosmic accident. At any rate, the building blocks of life are present throughout the universe, but scientists have yet to find them in the right combination and environment. The Kepler Space Telescope was designed specifically to search for alien planets. Kepler identified over 2,600 exoplanets during its 10-year mission. And one of its findings? Earth-like planets are not that rare.
Kepler discovered three important things. First, planets with small masses, or rather small radii, are common, far more common than giant planets. They're so common, in fact, that on average, every star has at least one such planet. It also discovered that planets don't particularly like being alone. They mostly exist within planetary systems. And it discovered something else, too. There are types of planets that we don't find in our solar system. Terrestrial planets, several Earth radii in size, which we refer to as super-Earths. We don't have them in our solar system, and they have new and interesting properties.
Researchers have strict criteria for what counts as an Earth-like planet. The central star must be similar to our Sun, and the planet must be in the habitable zone. The astronomers draw on data from the European space probe Gaia in their search. Gaia is measuring the position, motion, and brightness of nearly 2 billion celestial objects.
Gaia is basically mapping out our galaxy. Gauss and others introduced geodesy into our world, and since then, we've precisely surveyed the surface of the land. And Gaia is doing the same thing for the Milky Way, determining the position and motion of nearly all the stars in our galaxy, and has made some very exciting discoveries in the process. For example, it's discovered so-called stellar streams, which enter the Milky Way from the outer region, the halo, possibly from neighboring galaxies. And they reveal that we're interacting with our neighboring galaxies. This is an exciting discovery. Each time a new planet is discovered, we rely on Gaia to tell us how far away it is so we can determine its total luminosity. Thanks to Gaia, we have precise data for the first time. It really is a revolution. It's like geodesy of the Milky Way.
The Gaia data are a vast treasure trove for modern astronomy. Scientists use them to create a three-dimensional map of our galactic surroundings. The measurements made by the Space Observatory form the basis for a comprehensive star catalog containing detailed information on all the celestial bodies surveyed. Gaia provides us with an unprecedented insight into the structure of the Milky Way and the properties of stars and their planetary systems. The search for Earth-like planets is simultaneously the search for answers to humankind's biggest questions. Where do we come from? And are we alone? Discovering other worlds, detecting early signs of life, and understanding the mechanisms behind it are what drives the researchers. But it's important to define exactly what we mean by life.
In all ancient, advanced civilizations, primitive states, early, complex societies, and this was a complex early Bronze Age, but it then took billions of years for multicellular organisms to evolve. So there seems to be a massive difference between single-celled and multicellular organisms. It obviously requires very stable conditions for a very long period of time for multicellular life to develop. Consequently, it could mean that the universe is full of single-celled organisms, but perhaps devoid of multicellular life.
The discovery of planet KOI 456.04 proves that there are solar systems out there similar to our own. A twin Earth in the habitable zone of its star. Its star, Kepler 160, resembles our Sun in terms of size and mass too.
It's a place that would certainly be worth taking a closer look at. But unfortunately, it's over 3,000 light years away. That makes things rather difficult. We'd really like it to be 100 times closer so we could assess the situation better. But it's nonetheless interesting that there are apparently Earth-like planets out there. What the surface looks like, whether there's water, and what the atmosphere is made of is another question.
The search for a planetary system similar to our solar system continues. Finding a carbon copy of the Earth-Sun system would be like winning the lottery. But even then, the planet would have to have a whole host of other properties in order for it to be conducive to life. And scientists still don't know how life originated on Earth.
There are many, many criteria that constitute a good planet. A scientist once said that good planets are very hard to come by. This has to do with the fact that we're only beginning to understand all the requirements that have to be met for life to exist.
Our Earth has everything necessary for life to develop and survive. It has the right size and is at the perfect distance from its star. Plus, it has a magnetic field and a stabilizing moon. The Earth has an atmosphere, and there's liquid water on its surface. And our Sun has just the right size and temperature. In order to give rise to life, a planet has to have gone through a complex developmental process.
How a planet formed is important as well. How much water was the planet able to store in its interior during its formation? What impacts was the planet subjected to during its early life? And what were the consequences? Was the planet able to generate a magnetic field that protects the atmosphere and surface from cosmic radiation, for example? All these aspects must come together perfectly in order to create the conditions conducive to life on its surface.
The Earth is able to hold on to an atmosphere thanks to its gravity, unlike Mars, which has too little mass. This atmosphere is not only required for life on land, but plays a major role in regulating the temperature. The energy in the interior of the Earth causes locked up water and carbon to be released via magma. A kind of recycling, without which life on Earth presumably would have died out long ago. 2/3 of the Earth's surface is covered by oceans, the largest ecosystems on our planet. The world's oceans generate about 70% of the oxygen in our atmosphere, and they're a source of food, energy, and raw materials. In addition, our Earth has an unusually large moon, presumably created as the result of a collision with a planetoid shortly after our planet's formation. That impact resulted in the Earth's axis becoming tilted to an angle of 23.4 degrees. This tilt is responsible for the seasons. The moon's gravity also stabilizes the Earth's axis, thus preventing extreme variations in climate. Higher life forms probably couldn't have evolved without a moon of this size. The fact that the Earth even exists in its present form is likely the result of a special journey embarked on by Jupiter and Saturn through the early solar system.
How did the planets in our solar system actually form? Well, things started out very different than they are today. Let's take a look. This is the current situation. Here we have the Sun, the terrestrial planets, and further out the gas giants, with the Milky Way in the background. But the situation was completely different back then. Sure, we already had the Sun, but Jupiter and Saturn were much closer to the Sun than they are today. In between, in this region here, there weren't any rocky planets yet, just planetesimals, basically rocky fragments no bigger than, say, 10 kilometers. Then something very interesting happened. Jupiter started to drift inward. We call this migrating, and in doing so, swept these planetesimals before it, like a shepherd driving sheep. And these planetesimals began to collide with one another, eventually forming the rocky planets we have today, like the Earth here. Under normal circumstances, Jupiter would have driven these rocky planets into the Sun, and we wouldn't exist. But fortunately, we have Saturn. Saturn was following behind Jupiter. And when they entered a so-called 3-to-2 resonance, Saturn forced Jupiter back out again. And they've been in their current orbits since then. In summary, we can count ourselves lucky that we have Saturn. It prevented us from ending up in the Sun.
Some scientists think that Jupiter's migration to the inner solar system may have stunted Mars's growth. Jupiter's gravity suppressed the planetoids in the vicinity of Mars in the early solar system. As a result, Mars was unable to find sufficient material to continue growing. The scenario of a Jupiter swinging like a wrecking ball through the inner solar system could also explain the younger age of the rocky planets. There was only room for them to develop there once Saturn caught up with Jupiter and dragged it back out, thus vacating the inner solar system once more. The gas planets grew at a faster rate than the terrestrial planets. At the birth of the solar system, the inner solid planets found themselves in a material-rich region near to the central star. But they could only fully form once Jupiter had retreated. Jupiter and Saturn don't have a solid surface. They consist predominantly of liquid gas. But the two giants have a multitude of moons, and life could have arisen on them.
Take the moon Enceladus near Saturn, for example. It's a small moon, 500 kilometers in diameter, with a thick ice crust, and apparently an ocean of liquid water beneath this crust. You can even see it because it has geysers. We have liquid water, we have energy, which is generated by so-called tidal friction. And it's very likely that we have a core composed of carbon-containing material. So we have three of the components needed for life, and what we also need is time. And we certainly have time. In other words, if these three components were sufficient, then we should expect there to be primitive life in the ocean beneath Enceladus's thick ice crust.
The Saturnian moon Titan has a diameter of 5,150 kilometers, making it larger than Mercury. It has an atmosphere and oceans of methane. Due to its local circumstances, it's possible that life could develop here too. Researchers see Titan as analogous to the early Earth. It's certainly one of the most interesting objects in our solar system.
The central question is, of course, has life originated elsewhere? Could life have developed somewhere else? Naturally, we have to clarify what we mean by life. When we say life, we mean life as we know it. Certain organic compounds that combine to make sugars, amino acids, up to DNA and RNA that create replicable organic compounds and ultimately something like us. Is this only possible on Earth, under the conditions we have here, or is it also possible under other conditions?
The evolutionary history and structure of our solar system apparently allow for certain places conducive to the development of life. And the two gas giants, Jupiter and Saturn, probably played a decisive role in this. They were responsible for organizing the planetary system into its current state. And the zone between Jupiter and Mars bears witness to this process, the Asteroid Belt.
The fact that Jupiter and Saturn migrated inward and then back out again is something we haven't known about for very long. But it was a key realization for understanding how the solar system became structured the way it is. The pair act like gigantic slingshots. On their migration inward, they first scattered the planetesimals outward to where the Kuiper Belt is today. And when they migrated back out again, they scattered the objects there back toward the inner region, where the asteroid belt is now. And that's the situation we have today.
The asteroid belt between the orbits of Jupiter and Mars contains everything from tiny fragments of rock to minor and dwarf planets. It's also referred to as the planetoid belt or main belt. This is where the majority of the remnants from the planet formation process reside. The gravitational proximity of Jupiter inhibits the formation of additional planets. The incomplete objects are a throwback to the primordial state of our solar system.
These objects are like time capsules of our solar system because they contain within them the primordial material used to create the solar system. By examining these types of planetary objects, we can draw conclusions about the sort of material that was around at the time and from which the planets formed.
Psyche is of particular interest in this context. The asteroid, which is 250 kilometers in diameter, is thought to consist almost entirely of iron and nickel. The lump of metal is similar to the composition to the core of the Earth, just much smaller. Psyche could be one of the original building blocks of our solar system, the core of an earlier solar system object. The asteroids in our solar system are witnesses to its creation 4.6 billion years ago. Most of them have a somewhat elongated shape. Their gravity isn't strong enough for them to form a ball. Over 1 million of them have been discovered to date, with thousands more being identified each month. The largest objects in the asteroid belt are spherical and are classified as dwarf planets, like Ceres, which was studied over a period of 4 years by the NASA probe Dawn. During its mission, Dawn approached the surface of Ceres to within 50 kilometers. The data gathered suggests the presence of an underground ocean. This makes Ceres a possible target in the search for life in the form of microorganisms in our solar system. Jupiter is not only responsible for spreading all these objects around the solar system, but thanks to its enormous gravity, it protects the inner planets from this rubble too.
We do ask ourselves what all these objects are. Was there once a large planet that broke up? We still have no definitive answer. But we do know that Jupiter stabilizes the asteroid belt. If Jupiter weren't there, the asteroids would disperse and probably collide with the Earth too. As it is, they stay where they are and don't bother us.
Beyond the orbit of the outermost planet Neptune stretches another region containing remnants from the birth of our solar system, the Kuiper Belt. It begins at a distance of around 40 astronomical units, that is 40 times the distance between the Sun and Earth, and stretches outward to 500 astronomical units. So the KBOs, or Kuiper Belt objects, can be orbiting the Sun at distances of between 6 billion and 50 billion kilometers. They take several hundred years to complete one orbit. The dwarf planet Pluto is considered a Kuiper Belt object too.
When you go beyond the orbit of Neptune, there are a huge number of objects that are composed primarily of gas, basically water ice. But that far out, other gases like CO2 and methane freeze too. So everything that we think of as a gas is frozen solid out there. And a whole host of objects have stabilized there that were left over from the birth of the solar system. There's a huge amount of material out there, and now and then it ventures into the inner solar system.
Most comets originate from the Kuiper Belt. If a comet approaches the Sun, the constituent gases evaporate and form a nebulous envelope, the so-called coma. Blown by the solar wind, two tails form that can reach several million kilometers in length. One composed of dust and one of plasma. In 1994, astronomers got the opportunity to witness Jupiter's gravitational power with their own eyes. The comet Shoemaker-Levy, named after its discoverers, came too close to the gas giant. Jupiter made short work of the comet, which scientists estimated to be 4 kilometers in size.
The strength of Jupiter's gravity was so great that it broke up into many small pieces like pearls on a necklace. Then they all crashed into Jupiter, one after the other. Jupiter doesn't have a solid surface, so they disappeared into the clouds, each throwing up a little puff of cloud, which looked like pockmarks on Jupiter's surface. And then they disappeared. That is how Jupiter swallowed up many of these objects, protecting us from them in the process.
Comets from the Kuiper Belt, which have an orbital period of under 200 years, are referred to as short-period comets. Another reservoir of celestial bodies is the Oort Cloud, which surrounds the solar system like a shell.
As far out as the Kuiper Belt, the Sun's gravitational influence is still such that the orbits of the objects there lie in the ecliptic, that is, the equatorial plane of the Sun. But when we get further out, the Sun's gravity is simply too weak, and then the objects spread out in all directions around the Sun.
Objects from the Oort Cloud regularly journey into the inner solar system too. The comets that originate from there have orbital periods of over 200 years and are therefore referred to as long-period comets. Scientists suspect that around a third of the objects there originate from former sibling stars of the young Sun. Finding a piece of this primordial material and studying it would be a dream come true for researchers. The Sun's stellar siblings are now long gone. They've moved on to an orbit around the center of the galaxy. As such, our current stellar neighbors didn't form together with the Sun.
Which stars are closest to Earth? First, there's Proxima Centauri. It's just 4.3 light-years away, which doesn't sound like much. But if I were to fly there with my shuttle or a rocket, it would still take me 150,000 years to get there. That's a really long time, but it's just a red dwarf anyway. So you can pretty much forget it. Not much farther away are Alpha Centauri A and B, a binary star system. Both are nearly as big as the Sun, so a good star system. We're still not sure whether it has planets, though. We haven't seen anything conclusive yet. And then there are a few others at distances of 6 and 8 light-years. But they're all just red dwarfs. 75% of all the stars out there are red dwarfs, and thus not really capable of having planets conducive to life.
How immense the distances in our solar system are is illustrated by the journey of the two space probes Voyagers 1 and 2. 35 years after its launch in 1977, Voyager 1 became the first human-made object to cross the outer boundary of the heliosphere, the region of our solar system subject to the influence of the solar wind and its magnetic fields. Meanwhile, the two probes have traveled a distance of roughly 20 light hours. But our neighboring binary star system, Alpha Centauri, is 4.3 light years away. For humans, and even for space probes, the nearest stars are out of reach. The two Sun-like stars, Alpha Centauri A and Alpha Centauri B, orbit one another. The pair are, in turn, being orbited by another star, Proxima Centauri, a red dwarf. Our cosmic neighborhood is dominated by such low-mass red dwarfs. Of the 64 stars within 15 light-years of the Sun, 49 are red dwarfs.
Red dwarfs have a mass of between 60 and 7% of the mass of the Sun. Nuclear fusion does indeed take place within them, but it happens much more slowly than inside our Sun, which means that these stars can live for a very long time, up to 100 billion years. To put this in context, our universe is roughly 14 billion years old, our solar system is 4.5 billion years old, but these stars can live much, much longer.
Proxima Centauri has at least one planet, Proxima Centauri B, the closest confirmed exoplanet to the Earth. The planet is located in the habitable zone and could have liquid water. However, its star exhibits flare activity that would be fatal for potential life. Scientists can only study our neighbors with telescopes. The distances are simply too great for anything else.
Realistically speaking, there's absolutely no chance of getting anywhere close using a conventional rocket motor. Time will tell if we can invent other forms of propulsion capable of doing so in the future. But I'm actually very pessimistic about the possibility of our children, or grandchildren, or great-great-great-grandchildren having propulsion systems capable of traveling such vast distances. A light year is roughly 10 trillion kilometers. A trillion is a million times a million. And you can't cover these enormous distances using a conventional rocket.
Our solar system is seemingly unique, at least in our immediate cosmic neighborhood. We live in an exemplary planetary system, moving through a peaceful and thus perfect region of our galaxy. And scientists have yet to discover anything in the vastness of space that could provide the basis for a similar origin story.
Our solar system is simply perfect for the development of life, and in particular, for higher life forms like us. Is this all just a cosmic accident? Well, our solar system might not be unique, but it's certainly very special, because it's in just the right place in our galaxy. It has Jupiter and Saturn, which protect us from the asteroids, and that migrated in just the right way in the beginning so that the Earth didn't fall into the Sun. We have the Moon, which stabilizes the Earth's axis. And it's thanks to this unique combination that we even exist at all. Great that it worked out this way.
Our creation story begins 4.6 billion years ago with the death of a massive star, a supernova. The shockwave compresses interstellar material and thousands of new stars are born, our Sun among them. With it, the solar system and planets form, in the perfect location and at the perfect time. Our solar system is one of hundreds of billions in our galaxy alone. Nonetheless, it's still something very special. On the third planet out, the Earth, life came to be. Perhaps a completely normal event in the vastness of the universe, or perhaps, instead, the unprecedented consequence of a lucky cosmic accident.